Welcome to the Seasons of the Sun, the story of the solar cycle. It's a story of wonder, of mystery, of discovery. And I'll be your guide. My name is Mark Miesch of Ceres and the University of Colorado and NOAA's Space Weather Prediction Center. As viewed from space, the Earth has been described as a pale blue dot, a fragile and serene oasis in the surrounding darkness. This is the view of Earth from Saturn, taken by NASA's Cassini mission in 2006. It's a picture of everyone and everywhere you know. But a closer look reveals that the space around the Earth is not as serene as you might think. If you had eyes that could see the invisible, you would see that the Earth is flooded by a continual stream of plasma from the sun, called the solar wind. A plasma is a hot gas, bristling with electricity and magnetism. The wind washes over the Earth. We live in the outer atmosphere of the sun. But we do have some protection. There is a magnetic bubble around the Earth that diverts most of the wind. This magnetic bubble is called the magnetosphere, our own protective sphere of magnetism. The wind blows all the time, but it is not constant. Occasionally, there are extreme gusts of wind triggered by solar storms. Colossal releases of energy. Plasma is scooped up from the sun and thrown out into space. 1 million tons of plasma at 1 million miles per hour. These are the most dramatic of space weather events. They're called coronal mass ejections, or CMEs. But plasma is not the only thing that the sun throws at us. Even the sunlight that warms our planet can take a dramatic and hazardous turn. X-rays are a form of light that our eyes cannot see, but the sun releases tremendous bursts of X-rays and explosions called solar flares. This is a movie of 2 solar flares, the second stronger than the first. The energy released in a solar flare is millions of times more than the most powerful nuclear bomb ever detonated. There are also showers of particles, mostly electrons and protons, that stream away from the sun far faster than even the fastest gusts of wind, following spiraling lines of magnetic force. This is space weather's version of hail. Wind particles and light, CMEs and flares, all of these things can have an impact on our technological society, damaging power grids, disabling satellites, confusing GPS navigation, diverting airline flights, disrupting radio communications, and endangering the lives of astronauts who are brave enough to venture outside the protective confines of our atmosphere and magnetosphere. Understanding and predicting the origins, manifestations, and impacts of these events make up the discipline of what we call space weather. But just as there is space weather, there is also space climate. This is a graph of the number of solar flares each year for the past 25 years. X-class flares are the most extreme, followed by M-class and C-class flares, which are less extreme but more numerous. You can see that some years have many solar flares and other years have few. If I were to graph other types of solar storms, like CMEs, you would see a similar pattern. These are the seasons of the sun, otherwise known as the solar cycle. Years in which there are many solar storms are called solar maximum. Years when there are few are called solar minimum. And this pattern of maximum to minimum repeats about every 11 years, though each cycle is a little different than the last. Solar maximum is space weather's version of hurricane season, and another one is approaching in 2024. But what is the solar cycle? Why does it occur? To address these questions, it's useful to go back in time and talk about how we discovered it in the first place. So this is a picture of the sun, a photograph taken by a telescope at Mauna Loa Solar Observatory on the Big Island of Hawaii. And the spots you see on the surface of the sun here are called sunspots. Now this is a picture drawn by Galileo over 400 years ago. Note the similarity between what he saw then and what we see now. He saw spots too. And note the detail of his drawing. how much it looks like what we see now. But Galileo wasn't the first to see a sunspot. The largest spots are big enough to be seen with the naked eye without a telescope, at least in principle. The challenge is to see them without hurting your eyes. But this is possible, especially if the sun is low in the sky near sunrise or sunset, and if there is smoke or haze in the air, as from a wildfire or fog. Most records of sunspots from before the invention of the telescope come from China and Korea. But there are reports from all over the world. Some are harder to precisely date and verify than others. But this is probably one of the oldest reports that can be precisely dated. It's from China in 165 BC. The Chinese watched the sun closely for portents, particularly when it came to the emperor. Here's another report saying that the sun was orange in color, suggesting that it was indeed viewed through smoke or haze. Sometimes the sizes of spots were compared to common objects, in this case, peaches. Some reports are more detailed than others. This is one that describes a spot that was visible for 4 days, which is reasonable given the expected lifetime of a naked eye spot. Here's another one that's quite detailed, and it anticipates the rotation of the sun, which was established by European astronomers 500 years later, seeing 2 spots that moved together along an oblique angle. This impressive sounding report is one of the first in Europe, and it comes from a Benedictine monk in England in the year 1128. And it comes with a drawing of 2 spots in an ancient manuscript. But the fun thing about this one is that a few days later, there was an aurora sighted in ancient Korea. So there are reports of an aurora on December 13th, 1128. Of course, these reports did not know about one another, but we now know that they are connected across space and time, that the spot viewed in England by this Benedictine monk probably gave rise to a CME that triggered the aurora that was seen in Korea a few days later. So the first people to view sunspots through a telescope were Galileo and his contemporaries in the early 1600s. And they devised means to project the image of the sun onto a screen so that they could look at sunspots without hurting their eyes. And so they watched the sun closely, and we've been steadily monitoring sunspots ever since, with one caveat. Within a few decades of the first telescopic observations of sunspots, the sunspots went away. They disappeared almost completely for 70 years. For 70 years, there were very few spots. And it's not because people weren't looking. You can almost hear the frustration and the longing in the reports from that time. Spots could hardly escape the sight of so many observers of the sun, as were then perpetually peeping upon him with their telescopes in England, France, Germany, Italy, and all the world over. This continued for 70 years. And coincidentally and a bit ironically, this coincided with the reign of King Louis XIV of France, who was known as the Sun King. So during the reign of the Sun King, there were almost no sunspots. And we now call this the Maunder minimum. But the spots eventually did come back. So fast forward about a century to a man in Germany named Heinrich Schwab. So he started out as an amateur astronomer, but he became more interested in astronomy and more serious about it. He sold his family business, bought a better telescope, and he put it on his roof. And for every day, weather permitting, for 42 years, he would dutifully climb the steps to his rooftop observatory, and he would look at the sun, again, through these projection techniques, so he wouldn't hurt his eyes. So he was actually looking for a planet. There was, at that time, some people thought there was another planet inside the orbit of Mercury. They called it Vulcan. So he was looking for Vulcan. He never found it, but he kept records of sunspots. And after about 20 years of this, he realized that there was a pattern, that the sunspots waxed and waned about every 10 years. And he correctly predicted the solar maximum in 1848. So this is what our sunspot record looks like. It starts in the just before around 1600, just after this 1600, and you can see the sunspots coming up and down approximately every 11 years, sometimes a little more, sometimes a little less. You can see the period in the 17th century with very few spots called the Maunder minimum. And then beginning in the mid-1700s, the observations of sunspots became a little more regular and more reliable. So we start counting solar cycles around about 1760, solar cycle 1. This plot here only goes up to about 2015. So here it goes up to solar cycle 24. Now we're in solar cycle 25. So we have other ways now of quantifying the solar cycle and following the progression of the solar cycle. For example, the graph of solar flares that I showed you before. But none has the 400-year history that the sunspot record does. So thanks to this long history, sunspots continue to be the main touchstone of solar variability, and in particular, the solar cycle. This is how we measure how the sun changes. But there are clever ways to extend the record back even further. So it turns out that during periods of high activity, magnetic activity on the sun, it actually affects the composition of Earth's atmosphere. And carbon that is encased in tree rings and air bubbles that are captured in glacial ice. By looking at those carefully, we can extend the record of solar activity back 10,000 years. And this record, long record, is not as reliable or as detailed as the sunspot record, but it does offer some more information. And one of the things it tells us is that the Maunder minimum is real, that there were multiple periods in the last 10,000 years when the activity of the sun was unusually low or unusually high for multiple cycles at a time. These are called grand minima and grand maxima. And it also tells us that 11 years isn't the only pattern you can find in this sunspot data. So you can also see that there's another pattern here of approximately, you can even see it in the sunspots, that approximately every 100 years, there's an upwelling of activity, that there's a waxing and waning of the solar cycles about every 100 years. And we even see signs of grand minima and grand maxima, evidence for these in other stars. We can look at other stars that exhibit magnetic cycles a lot like the sun and learn about the sun by looking at stars. So all this is fascinating, and we could talk about it for hours, but I wanted to go back in time again to about 1800. So this is Baron Alexander von Humboldt, the most famous explorer and scientist in Europe in his day. And the painting shows him in what is now Ecuador during his expedition to Latin America from 1799 to 1804. So there are many exciting stories from this expedition, but the one that matters most to us is he brought a device with him called a magnetometer. So this is like a compass. It measures the magnetic field of the Earth, but unlike a compass, it can measure the up-down direction as well as north-south. So when Humboldt was in Peru, he discovered the magnetic equator, the midpoint between the north magnetic pole of the Earth and the south magnetic pole of the Earth, where the magnetic field is horizontal. But he also noticed something else exciting, that every now and then, his magnetometer measurements would go crazy. The magnetometer would go wild, and he called these periods magnetic storms. So he goes back to Europe, and he tells people what he saw, and everybody gets very excited. So this triggered what has been called the greatest scientific undertaking the world has ever seen. So this was the Magnetic Crusade. There's a nice popular account of it in Stuart Clark's book, The Sun Kings. But this inspired scientists, mostly in Germany and England, to build magnetic observatories all over the world. Some of these are still standing. Here's one in Toronto. So they built these observatories in order to map out the Earth's magnetic field and to study these magnetic storms. So some of the people involved are names that might sound familiar. In Germany, they were names like Gauss and Weber. Mendelssohn Bartholdy is the father of the famous composer. In England, it was Edward Sabine and John Herschel. And an interesting aspect of this is that Edward Sabine's wife, Elizabeth Leaves, was also a scholar. And in 1849 to 1852, she set out to translate Humboldt's magnum opus Cosmos. So this was a book that included some scientific discoveries from his expeditions, but science more generally. And you can still buy this book on Amazon. So you can buy Elizabeth Leaves' translation of Humboldt's book on Amazon. But when she was writing this, when she was translating this, her husband kind of looked over her shoulder and noticed something fascinating. So Heinrich Schwab had published his work on the solar cycle about 6 years prior to this, but not many people knew about it. It was written in German, and Sabine didn't know about it. But while his wife was translating Humboldt's book into English, Humboldt had an account of Schwab's sunspot cycle. And an account by a famous scientist, he brought it to a much wider audience, and in particular, an English-speaking audience. And Edward Sabine saw this sunspot cycle and recognized the pattern immediately. He recognized that he had measured geomagnetic variations, so the magnetic field of the Earth that he was measuring followed this same cycle, going up and down about every 10 years or 11 years. And so this was huge. People had been speculating that there was some connection between sunspots and the Earth for over a century. But this was the first real evidence that something on the sun could impact something on the Earth. The Earth's magnetic field changes with the sunspot number. So it didn't stop there. This brought into another fascinating connection. So people living in high latitudes have been observing the northern lights ever since they first set foot in those lands. The written records of aurora go back thousands of years, but the sightings must go back much farther. They're hard to miss. And it had been known since the mid-1700s that the northern lights disrupted compass needles. So if you were on a ship under the northern lights, you couldn't navigate by compass. So if there is a connection between sunspots and the magnetic field of the Earth, then that could mean there might be a connection between sunspots and the northern lights or aurora. And this is in fact the case. It wasn't really established or widely accepted until the work of Christian Birkeland in the 20th century, the early 20th century. So this is exciting, but before leaving this topic, I wanted to bring in another way that people have been observing the sun for thousands of years, and that's eclipses. So this is a picture of an eclipse, and an eclipse lets you see a part of the sun that you don't see in other circumstances. It's called the corona of the sun. Corona is Latin or Spanish for crown. So the outer atmosphere of the sun, the corona, is about 1 million times dimmer than the disk of the sun. So if only 1% of the solar disk is showing, then the corona is lost in the glare. So there's an eclipse, as many of you have heard in this audience, passing the United States in 2024. And I highly recommend that you make the effort to get to the path of totality so you can see the total eclipse, because there's a big difference between a total eclipse and 99% eclipse. But as I said, this is another way to learn about and follow the science of the sun. So in fact, the first CME, the first record of what we now think is a CME, occurred during an eclipse in 1860. So this is a drawing made by an astronomer in Spain. And this big blob on the lower right, we now think is probably a CME in progress during the eclipse. And the interesting thing about this is that the eclipse path went from Spain across North Africa, and there were other drawings of this event. And you can see that blob moving outward as the hours pass. So we now, they didn't know it at the time, but we now believe this is probably the first record of a CME. And the eclipse that I mentioned will pass over the US in 2024. This will occur near solar maximum. So if we're lucky, we might see a storm like this. It's unlikely, but we'll see a good show in any case. So in the time I have left, I wanted to say a few words quickly about our modern understanding of the solar cycle. So the sunspot number now is maintained by the World Data Center for the Production, Preservation, and Dissemination of the International Sunspot Number at the Royal Observatory of Belgium. So that's shown here by the black line. There is now international collaboration on monitoring the sun and quantifying the sunspot number. The gray curve that you see, sort of the gray range here for cycle 25, is from an international prediction panel from NOAA, NASA, and the International Space Environment Services. This panel was convened in 2019, and they synthesized nearly 50 different predictions for solar cycle 25 into a single prediction with a range. And they produced this prediction, and they predicted that the cycle 25 would lie somewhere in that gray range. As you can see, the sun is defying us. The sun is stronger than predicted. The current cycle is there are more sunspots than we thought there would be. But we still expect cycle 25 to be a pretty average cycle compared to other cycles in the past century. So we now know that sunspots are magnetic phenomena. So the image on the bottom here shows what sunspots look like in visible light, a lot like Galileo's drawing from 400 years ago. But we can now measure the magnetic field on the surface of the sun from 93 million miles away, and that's shown on the top. So here, white is magnetic field that pokes out of the sun. Black is magnetic field that points into the sun. So the interpretation is as shown here on the lower left, that you have lines of magnetic force that poke out of the sun, curve around, and then poke back in. So this means a few things. This means, first, that sunspots often come in pairs, one black and one white, as viewed in the magnetic field on the top here. And it also means that sunspots are places where magnetic energy is passing through the solar surface. Magnetic energy is created in the inside of the sun, and then in sunspots, it's passing through the surface to energize the solar corona and power these solar storms like CMEs and flares. If you look at these observations in clever ways, you can find some striking patterns. So we call this the butterfly diagram that shows the magnetic field poking through the surface of the sun, like the last slide, but here, instead of black and white, inward and outward field is here colored blue and yellow. And we call it the butterfly diagram because it looks like there's a line of butterflies flying from left to right. And so we've taken an average over all solar longitudes so that we can highlight how the magnetic field changes with latitude and time. The time spans about 40 years, a little less than 4 solar cycles. So let's pick a time. Let's start with 1997. So you see from the sunspot number on the top that this is solar minimum. Here, the North Pole is yellow and the South Pole is blue. So this is like a bar magnet, as shown in the lower right here, where you have a north and a south magnetic pole. But in the next few years, the magnetic field becomes more complicated. Blue and yellow dots appear at latitudes of about 30 degrees in the northern and southern hemispheres. So these are sunspots. This is the magnetic field passing from the inside of the sun up through the surface like we saw on the last slide. With time, those spots go away and new spots appear. On average, those spots each pair of spots lasts only for a few days, for a few months, but on average, as they each come up, they're slightly closer to the equator. And the new spots that appear are, with every year passing month and year, are slightly closer to the equator. And after about 11 years, they reach the equator and then they go away. And then there's another solar minimum. So now this is 11 years later in 2008. And now we have a solar minimum, but the magnetic field, now the North Pole is blue and the South Pole is yellow. So the magnetic field has flipped. The bar magnet of the sun has flipped. So there is an 11-year sunspot cycle, but a 22-year magnetic cycle, because it takes 2 flips to get back to where it started. So a close look at the solar surface reveals intense turbulence. So these are giant patches of seething plasma. Each of these patches is almost 1,000 miles across, or 1,500 kilometers, and only lives for about 15 minutes before it is subsumed into the maelstrom. So the solar cycle, the order of the solar cycle, somehow emerges through this chaos. And this is only the tip of the iceberg, so to speak. We believe that under the surface, below the surface of the sun, that it's just as chaotic. So this is a computer model of what might be happening below the surface. So you can see the swirling currents of plasma shaped by the rotation of the sun. So on the right is a view down from the North Pole, but I'm going to focus on the left. So here you see what's called convection. So the warm fluid rises, cool fluid sinks, like a pot of soup on the stove. So as plasma is heated, it rises toward the surface, and as it's cooled, it sinks down. And you can see the patterns of this convection are different near the equator than they are near the poles. But if you look closely, you can see something else, that the patterns of convection are moving from left to right near the equator, but at the poles, they're moving from right to left. This is rotation, but not like the Earth. The equator is spinning faster than the poles. So we call this differential rotation. So we're now in a position, we have some of the concepts we need for a whirlwind tour of the solar dynamo. The dynamo is the name given to the process that creates the solar magnetic field, and consequently the solar cycle. So the energy in the magnetic field comes from the energy in plasma motions. You have this convection and differential rotation that produce organized wreaths of magnetism with opposite signs in the northern and southern hemisphere. Loops of magnetism detach from these wreaths and rise like hot air balloons, poking through the surface as sunspots. This creates a mess in the corona, as shown in the lower right, a mess of magnetic field. This is actually a movie of Solar Cycle 23 that I'll play now. The green and blue, as before, indicate the direction of the field, whether it's pointing out or in. And the thing to keep in mind here is note that the green is up. That's purple, I guess, green and purple, and the purple is down. So I'm going to play the movie. And so this is actually Solar Cycle 23. And you see, as the magnetic field emerges through the spots, it is reorganized by the sun. And this reorganization of the magnetic field causes the field to flip. So this reorganization happens through a complex interplay of global circulations, both on the surface and inside the sun. So remember, green was on top when we started, and now we're coming to the end, and the magnetic field of the sun has flipped. So that's our current understanding of the solar cycle, but there's much we still don't know, in particular the details of this reorganization process after the magnetic field has emerged. We still have a lot to sort out there because a lot of this happens below the surface of the sun where we can't see. But we have tools now that are beyond the dreams of our scientific ancestors, even the most prescient like Galileo. We keep a continuous watch on the sun with a worldwide network of telescopes and a growing fleet of spacecraft. We can even now see inside the sun in a sense, measuring how the sun reverberates with sound in a discipline called helioseismology. Computer simulation has become the third pillar of science, taking its place, along with theory and observation, as a distinct and powerful way to learn about the natural world. But that's not all. We can now teach machines to recognize patterns in space weather and warn us of impending changes and impending danger. Exploring mysteries of the solar cycle links us to the curious sky watchers who have wondered about sunspots, aurora, and eclipses for thousands of years. But progress is more important now than ever. The impact of space weather on our daily lives is growing as our society becomes increasingly dependent on modern technology. Accurate prediction of space weather hazards requires understanding. So we will continue to venture boldly forth in our age of discovery.